Good morning, and welcome to session 6A on synthesis. So we're going to have 5 talks in a session. A couple of them will be remote, and so let's first welcome Ziteng Wang, who's going to tell us from batch to stream automatic generation of online algorithms.
All right. Can you hear me? Okay, nice. Thanks for the introduction. Hi everyone, I'm Ziteng Wang from UT Austin. Today I'm going to present our work from batch to stream automatic generation of online algorithms. Let's begin with a little bit of background about online and offline algorithms here. So offline algorithms are used in a traditional batch processing setting where a large chunk of data was first put into a database, and then they will be processed in a fixed interval and getting some results periodically. On the other hand, online algorithms are used in a stream processing setting where we will process and analyze the data in real time. We'll put it into a continuous data processing stream, and then it will always get us some live result. So stream processing can be useful in some time-sensitive computations. For example, it could be like fraud detection for financial companies, marketing and sales analytics, and finally inventory management, so on. And we see like increasingly popular frameworks that adapting this kind of stream processing like Apogee Spark, Storm, and Flink. Here's an example of an offline algorithm computing simple mean. So here, let's say we wanted to compute the simple mean for 0, 1, 2. And here, we know the answer is 1 because we will first compute the summation S to 3 and over by the length of the list 3. On the other hand, let's say if the list is updated with a new item 3 here, then we will need to recompute the sum and length all from scratch. On the other hand, the online version is a bit different. It has 2 parts, a Python function called mainOnline and an initializer. I'll get into initializer in a second. Let's first take a look at the function signature of mainOnline. So V denotes the value of previous mean, and then N is the number of previously processed items. Finally, X is the new item. So the initializer basically is the value of V and N before we even processed any element in the stream. Say that's the state after processing 0, 1, 2. If we want to compute the new mean when adding 3 to the stream, then we can incrementally do this by first updating new S and then having new N. And here, the complexity of the offline algorithm is O of N because you did a linear scan over the list, whereas the online algorithm will only be a O of 1 because we just update the element, just update one element. So in our work, the problem statement is as follows. The offline program is a program that transforms a list access into a result P of access. And then the online thing will be a bit different. That's something we call online scheme, which is a tuple of I and P, where I is the initializer and P prime is the updater, which is usually something we call online program. But really, we need the initializer to make the online program work as well. Our problem statement here will be, given an offline program P, find an online scheme S, such as P is equivalent to S. And here we have the offline-online equivalence here. Basically says that our output of the offline program should match the outputs of online program when we are doing a fold left over the stream modeled as a list. So what is the challenge here? Well, take a look at this simple example. This is computing simple variance in a 2-pass style. And interestingly, the online algorithm of variance is actually coming from an old paper in 1960s. And this is called actually Welford's algorithm. And if you take a look at the Welford's implementation, it has quite complex nonlinear expressions. To make things even worse, we haven't known anything about like what are the additional states needed here. So we need to figure it out. So in our work, we use we have 2 parts that basically work around these 2 problems. So Opera will first use a static analysis to figure out a relational spec, and I will introduce that later. And then the relational spec will be helpful in constructing the initializer, and then use compositional deductive synthesis to figure out the online program. Let's start with the relational spec. So here is an example of the same program variance but written in our functional intermediate language. And then here's the relational spec opera inferred. Here, the relational spec is something we call the relational function signature. It basically consists of two parts. The first part is showing the first column of relational spec, which is the parameters, the function signature of the online program. And secondly, it also says what those arguments actually mean here. So the specification column is exactly what the semantics is. So for example, as is just fold left plus over access. How do we infer the relational function signature? We use a lightweight static analysis to figure out all the offline expressions in the variance program. Offline expressions are expressions that involves the list input as one of its arguments. And then we will figure out like each parameter with its specification precisely highlighted in the program. And since I promised you we can get the initializer, actually we can just get it for free, because we just construct the initializer by evaluating the expression on the empty list for each specification shown here in the relational spec. And you might have a question like, what if I divide by 0 then? Well, we use the notation of safe division that basically all the division by 0 will result in 0. So that's all the zeros we get from evaluating expressions here. So now we have the relational spec from static analysis. We're ready to take a look at how compositional deductive synthesis work. The key idea behind our synthesis methodology is that we can redefine equivalence in terms of equivalence module RFS. And intuitively, that means that an online program P prime preserves the RFS. Then we will say like this is inductive modulo RFS. Let's take a look at the formal definition here. So formally speaking, this is online program P prime is inductive relative to RFS phi if the following Hoare triple is valid. In a high level, that means that if the state variable y has some correspondence to xs, then after getting like a y prime, which is the updated state variable, we should get some correspondence to the new list xs prime. So with that definition, we show that the equivalence can be redefined as follows. So the online scheme S will be equivalent to the original offline program P if, first, its initializer is consistent to the RFS, and secondly, P prime is inductive relative to phi. So we can redefine our synthesis task as given RFS, the relational function signature phi, and then construct P prime that is inductive modulo phi. And since I already tell you like how do we construct the relational spec phi, it's just something we can just figure out like the program P prime. And this reformulation facilitates deductive synthesis. Let's begin with the first part of the learning part, decomposition. So the decomposition idea is based on two observations. The first observation is that offline program and online program share this the same high-level structure. So we can infer a sketch of online program to reuse that structure. Secondly, online expressions are independent to each other. So we can just decompose the online synthesis problem into independently solvable tasks. Well, here's an example of sketch generation. In the same variance program, we just replace offline expressions highlighted here with unknown hosts showing the sketch here. And then the original expression is used as specification. Just to recap, the offline expression is really like the expression that uses the input list access. And now we have a sketch, we can synthesize the expression. The high-level idea behind expression synthesis is that we will replace offline expressions with equivalent online expressions. And here, we will use the deductive synthesis approach to find such equivalent expression. You might recall that the idea is the relational spec enables us to use logical reasoning for sketch completion. So how do we do this? Well, this is based on the following task description. So we wanted to synthesize an expression E prime such that E prime is equivalent modulo RFS to the offline program. So what on earth is equivalence modulo RFS then? It basically means that under the assumption of the relational spec phi, we can have the online expression E prime equivalent to E when we are updating XS to be XS concat X. Here is an example. Let me show you how S plus X is equivalent to the specification for unknown box 1. Left-hand side is easy, just like plug in E prime. And the right-hand side will be, we are having like a fold left plus over XS plus X. So we can use the definition of fold left to unroll one step. And then the specification tells us S plus X is equal to the expression, which concludes the example. The idea behind finding such an E prime is that we can find the implicate of form some program equal to a term, where the term is over the online parameters. Here's the concrete example. So phi is the relational spec we inferred from the input program. T is the specification for the synthesis task. A is the definition for fold left instantiated on plus. So we found that the conjunction of phi, T, and A actually implies the online expression. So we are down here, that's nice. However, you might notice that in my formula, there's many like higher order combinators, which could be a problem because we need to encode everything into like a SMT solver in order to find such implicate. So please refer to our paper for the detailed workaround. We use fresh variables to get over this problem. But the observation is that sometimes we cannot find such implicate. So in that case, we will try to under-approximate the implicate, and then we will use some trick to mine useful expressions from the input program. And this mined expression will be useful in later search. By searching over like the template, we can find the final implicate. That's how we combine symbolic reasoning and search. So finally, how well does our technique work? Well, to answer this question, we collected 52 programs from 2 sources, statistics and auctions. So the statistic benchmarks comes from popular GitHub repositories, SciPy and onlinestats.jl, and there's examples like skewness, variance, geometric mean, and auctions are those programs from a popular benchmark suite called Nextmark for stream processing applications. Example including like generating bidding reports, monitoring new bidders, and so on. Here we studied the AST size of those programs in these 2 categories. For statistic functions, you have like a slightly or significantly larger online program due to the complexity introduced by cubic and quadratic expressions. But for auction programs, they usually stay relatively the same. Okay, so we evaluated Opera against 2 baselines, CVC5 and Sketch. Those are the state-of-the-art SyGuS solver with nonlinear arithmetic support. As you can see in the plot, Opera synthesized 50 out of 51 online schemes within an average of 25 seconds running time. And it significantly outperforms the existing baselines here. And we studied 2 ablations here. The first one is Opera no decomp, where we just turn off compositional synthesis technique. And the second one is called opera no symbolic, where we disable symbolic reasoning technique and then but keep like decomposition thing on. And here's the result. As you can see, disabling either of these key techniques will have a significant negative impact on opera's performance. So that is opera, and I'm really excited to give this talk as this is my first talk. Thank you so much. And I'm happy to take questions.
Okay, I have questions.
Yeah.
So if I understand correctly, the online algorithm you synthesize is prepend an element to a list. What if I want an algorithm that append an element to a list? Will your approach still work?
So the question is, right now, our problem statement assumes that the stream setting will always append like the element at the end. So will it work if I just insert anything at the beginning? I think,
yeah, or the other way around.
Yeah, exactly. Okay. I think this question is really asking like whether this same technique can be used in some general incremental computation scenario. Yeah. Because in a streaming problem statement, you always put the item at the end. So I think probably we need some adaptation to say, to make the thing work. But I can imagine in some incremental computation scenario, there might be still some relational specification needed. So in that case, if you have some relational specification, we might be able to like reuse some of the technique. And I don't think there's fundamental reason that prevents you from doing this.
Okay, so another question that you extract some auxiliary values by a statistical analysis. I'm wondering, is there some completeness guarantee such that for any algorithms, for any online algorithms, it's enough to just use in this set of auxiliary values?
That's a really good question. So the question is whether our static analysis thing will impact the completeness of our algorithm.
Yeah.
So I think it can be viewed as this. So our approach is really like putting any information you might needing from the offline program into like the state variables. So in that sense, I think we are really like saving everything we potentially needed. And we always only remove something if in the synthesized program, we ended up not using any of them. So in that sense, I think you're still having like the complete information you may have. Okay. So in that sense, I think it won't affect the completeness issue.
Okay,
does that answer? Yeah, thank you.
Hi, thank you for the nice talk. So my question is about the sort of distributed setting. So in your setting, you're synthesizing the update function basically on a list processing program. Have you thought, so if you're doing something like synthesizing like MapReduce programs, you might also want this update function to satisfy something like some sort of commutativity, associativity properties. Have you thought about if your approach generalizes to that setting?
Yeah, that's right. I think there's definitely like something we can do, and actually we are considering of like expanding the problem statement to be more like a parallel computation or divide and conquer style computation. I think in that sense, since again like stream processing thing is still a very like specialized and restrictive form of both incremental and parallel computation. So I guess right now I don't have like many insight about this, but definitely this is an interesting and challenging direction that I'm eager to explore.
Okay, thanks.
Yeah.
That was a wonderful talk. Thank you. One thing I was curious about is in some of your first examples, you had these like explicit for loops in your inputs, but then in the later ones, your RFSs just included these higher order combinators. I was wondering if you had support for like these for loops as part of your RFS.
Oh yeah, that's a fantastic question. So right now, we take Python programs with imperative loops as input, but we have like some rule-based translation to basically translate that Python program into higher order combinators. And in principle, I think it's possible to basically translate with some existing work about transpiling imperative to functional code. But right now, since our application scenario is very restricted to the streaming application, our rule-based translation is applicable on our on the benchmark side. And yeah, I think you can definitely handle that.
Great, thanks.
Yeah.
Hi, great talk today. It was
Thank
very
you,
clear.
Aaryan.
Thank you. So my question, I think, is a follow-up on Yuepeng's question on completeness, really. So I think, so my question is, what is the class of batch programs that this would actually work on, right? Because in all of your examples, these offline expressions that you're replacing, they're themselves folds. They were all folds, right?
Yeah.
And it feels like that is maybe the key to why these intermediate values were the only ones that you needed, right? And you could actually reproduce in this online fashion. Or am I wrong? Or maybe you can give me an example of a program where this is not applicable.
Right. So I think to answer that question, it can be answered like in two. Okay. So sorry. Let me repeat the question first. So right now it seems like all the programs are written in some fold left form, and this is in like a functional. So it's really could be kind of my technique could be specialized for this program, and well. It can be answered in two ways. So first, whether the language, the functional IR is expressive enough. So in practice, when we collect the benchmark, we don't have like the functional IR in mind. So we just like collect all the benchmark we can have from those two categories. And in practice, we found that we can always express that in this functional IR. And secondly, there's a publication in functional program that basically discuss the expressiveness of a small calculus with a fold. So it looks like the program, the language should be expressive enough.
Mm-hmm. But for example, if it was a quadratic program in the first place,
right? So we
cannot do it, right? I mean.
Sorry, could you clarify like what is the quadratic program?
Well, like if the batch program had to go over the list like quadratically a number of times, it seems like it would not work, right?
Well, because like for example, if the input stream is like a stream of lists, is that what you're asking? Like it's no longer like a numerical one.
We're sort of out of time. Let's can we take that offline? Yeah, sorry.
Okay. Thank you.